Hi, I'm Dan Winograd-Cort. I work with Paul Hudak at Yale, and this is Settable and non-interfering signal functions for FRP. So we'll start with the context of functional reactive programming and what we're doing. So functional reactive programming is about programming with continuous values and streams of events. Particularly, we're dealing with arrow-wise functional reactive programming. And this ends up looking like drawing signal processing diagrams. So on the left, you can see a signal function as a diagram, where we represent the signal function as a box, and we have lines going in and out representing streams of values. And on the right, we have the great arrow syntax in Haskell, where it looks almost the same. Very convenient. So this has been used already in Yampa and Nettle and Utopia for things as varied as robotics to networking to sound synthesis and music. So if we look at arrows in a little bit more detail and how we're going to represent them for this talk. So any of you who are very familiar with arrows, you don't really need to pay attention for the next few minutes, but we can start by looking at event-based versus continuous arrows and streams. So typically, we think of streams as continuous, and so we'll represent it this way with a box and pointers, just like we saw on the last slide. And by default, if we don't know if it's event or stream, we'll still use this notation. Specifically for event-based arrows, we'll use this alternate red lines with the circles at the end to represent that it's an event. An event is just, it's a stream that's only defined at particular discrete values rather than continuous. So we have some standard arrow operators, which you may have seen before. So there's the R operator for lifting a pure function to an arrow, and we'll represent pure functions as circles. We can do partial application and just apply one stream of multiple to a signal function. We can also compose signal functions by stringing them together, and even create feedback loops, which in this case is an arrow that goes from the right to the left. So you can extend arrows even further. We can have stateful arrows. So in this case, we have a delay function. And I represent this in this way to indicate that there's a unit time delay going through this signal function. So a data value comes in, and the one that comes out is from 1 unit in time previously. It's notable that if you're dealing with a totally continuous semantics, then this unit delay approaches 0. And so we will kind of just use delays once in a while and assume they have no real impact. Interestingly, when you use delay in conjunction with loop, with that feedback, you can create state. By having a delay operator feedback into itself, you can retain a value over time. Additionally, we have arrow choice, which is going to be integral to this later. But we represent this with this diamond there, and we say that if we have a value that is either, say, a left or a right, then we can say that left of a signal function is a signal function that interacts with that value only when it's left and not when it's right. So running the signal function becomes a dynamic decision. We also have higher order arrows, oftentimes represented as switch in functional reactive programming and arrow-wise functional reactive programming. We represent that with the black diamond here. Higher order arrows are inherently dynamic. They allow us to take a signal function, like the SF here, and replace it with a totally new signal function that's on the stream at a given time. So it would be a discrete stream of events of signal functions that could replace the one that's currently there. So this makes the arrow structure inherently dynamic, because rather than having a static arrow structure, we can replace things. Now, interestingly, that's what a monad is as compared to an arrow. So arrows with switch are equivalent to arrows with arrow apply, which is just equivalent to a monad. And so switch takes away that static structure. Now that static structure is really good for optimization purposes. It can be really good for embedded systems that have constraints on what types of programs can run. So why have switch if that's just equivalent to monad? Well, so in some cases, you really do want that higher order signal expression. Sometimes the arrow is the right style that you want to use, even though occasionally you need some sort of higher order monadic design. But also, people use switch. It's used in a lot of places as kind of a really strong version of choice. It allows us to start and stop signal functions because we can take part of our arrow structure and just remove it when we don't need it anymore, or add something into the arrow structure that we didn't want there before. So what am I contributing? What are we doing here? Well, we're saying that this kind of multi-use purpose for switch doesn't make a lot of sense. And so we're going to take this switch-like behavior, not the real higher order monadic part of it, but this power choice part, and we're going to replace it. So specifically, we introduce something called resettability, which allows signal functions to act as if they've just been started. And we introduce a new law to add to arrow choice called non-interfering choice, which increases choice's power to behave a little bit more like switch, to allow signal functions to start and stop. And additionally, when we add these, we're going to get two extra benefits. We're going to get generalized settability out of our idea of resettability, and we're going to get arrowized recursion, which is a slightly different way to do recursion with arrows. So let's look at an example. So say we have an integral signal function. They often come bundled in with an FRP system. And we want it to reset itself every time a given event comes along. Well, for anyone who's programmed with higher order arrows and switch before, this should be really straightforward. What we're going to do is we're going to have our regular integral. And every time the event comes in, we're going to map over it and put on that stream a brand new integral signal function and just switch into it. And the brand new integral signal function has totally fresh state and will act like the integral just reset itself. And that works. But we ask the question, can we do this without switch? Sort of. So here's a way we might go about doing it. This looks a little bit more complicated. Here we have the integral. Look at the top wires, and it's going to subtract something. And that value that it subtracts is basically, if there's an event, we're going to save the current value of the integral, and otherwise we keep the previous value. We use that delay with feedback system to create state. And we're subtracting that out. Now this works because integral starts at 0. And because of the way it keeps track of state, we can subtract things and it acts like it's resetting. But this is terrible. It's totally inelegant. It doesn't scale. It happens to work with integral, but it doesn't necessarily work with any other signal function. So if we try and think about it, what's the real problem here? Well, the real problem is that we want to access the state inside the integral, but we can't get in there. So we want to think about what is in an arbitrary signal function. Well, if we want to access state, the only way to get state in an arbitrary signal function is with the loop and delay method that I mentioned earlier. So let's take a look inside integral. It's probably implemented somewhat like this. You take the input, you multiply it by some dt, you add it to whatever was previously calculated, and that's the output. So if we look at it this way, what we really want to do is we want to get into that delay. If we can reset that delay, then the whole integral will act as if it's been reset. So what if we look at just a simpler example then? What if we try and create a resettable delay? Well, we can do that. So here, when there's no event, this behaves exactly as a delay. And when there is an event, we use the arrow choice in order to say, instead of returning what the delay returned, we'll just return a constant value of the initial, constant initial value. And so now we ask the same question we asked before with integral reset. Does this scale? And interestingly, it does. There's a whole transformation that I outline in the paper and don't have quite enough time to go into now that will take any arbitrary signal function and will turn it into a resettable signal function by transforming all of the compositions and the loops and the delays, etc. And in fact, we can take this one step further. We don't need to just reset a delay or a signal function, but we can make a signal function totally settable. So here's the notation we use for that. The top wires are the regular wires for the signal function. And the bottom ones, we have an input state event, which can be used to set a state, or there's a default reset value to reset a state. And then the output is whatever state that signal function currently contains. You can use this to store that somewhere and pass it back in the future. So rather than going into the transformation, as I said, I'll instead look at the settable laws. So there are 3 laws we define for settability. The first is the identity law, which basically says that if you don't ever provide an event of a new state and you ignore the output state, then the signal function will behave as if it weren't being settable. Second is the uniformity law, which says that if you take the output state of a settable signal function and immediately feed it back in consistently and constantly, then basically what you're doing is setting the state to itself, to the current state, and thus the signal function will behave as if it weren't settable. And lastly, if you always feed in the default reset event, in this case we feed it into just a delay signal function, then it will act like the initial value, in this case the initial value of the delay. So we can go back to the integral reset example, and now it looks a lot like the switch version. Right? We take that input event, we map over it the default reset state, and we send that into a settable version of integral, and it works. And the key thing here is that we no longer need the overkill of lifting a whole signal function onto the signal level just to use switch to concretize it back into the arrow structure. The structure of the arrow remains static throughout. So let's look at another example, a slightly more complicated one, where instead of just trying to take our integral and reset it, what we want to do is pause it. So under a given condition, the integral will run, and when that condition doesn't hold, the integral won't run. We just want it to pause, return the value that it's calculated so far. So without switch, we might do it like this. We take our integral, we get the delta change that it's accumulated in this last moment in time. We put it through this function that basically says, well, if our condition holds, then we add that delta to our previous result, and otherwise we return our result. Just for the record, that get delta is just going to subtract out previous value. So this works, but it's deeply unsatisfying because it's going to be calculating the integral regardless. On every moment in time, whether the condition is true or false, the integral is calculated. So you might say, well, we can fix this with switch. And here we go. Here, I'm abusing the notation slightly so that our condition is now an event of true or false. And I only do that so that the diagram can be a little simpler. But when you get a true event, you switch out for a new version of the integral. And when you get a false event, you switch out for a constant value. We've got this extra v floating around because we need to keep track of what's been accumulated so far. But this works, and it's fairly straightforward. But it's still unsatisfying. Because why do we even need switch? Can't we use arrow choice? Can't we say, if the condition's true, run this signal function, otherwise run the other one? Well, we can't exactly. That's because of how arrow choice is defined. So these are the arrow choice laws. In particular, we can look at the middle one, exchange here. And so diagrammatically, this will look like this. It says that if you have a value that's either left or right, and you calculate the left value of f and then the right value of g versus the right value of g and then the left value of f, then these are equivalent. But you'll notice that f and g are not quite the same here. This isn't commutative, right? In fact, g is a circle. G is a pair function, whereas f is a signal function. So why is that? Why is an arrow choice commutative? Well, it has to do with arrows themselves. Arrows can have effects, and thus the order of putting together f and g can have an effect on the arrow itself and how it behaves. So in many FRP applications, this order doesn't particularly matter. And even when it does, I'm not asking for commutativity in general. I'm just asking for commutativity in arrow choice. And if we allow commutativity, in fact, if we restrict it to that, then we can do something interesting. So in fact, I'm going to go one step further, and instead of just commutativity, I'm going to demand non-interference. We'll see the benefits of this in a minute. But so what non-interference says is that if you have a value coming in, specifically a right value, you assert that it's right, and you send it into a function through arrow choice that only accepts left, then the whole thing will behave, the whole arrow will behave as if that function weren't even there. So this is kind of interesting, because now when you take a particular branch of arrow choice, the other branch acts as if it doesn't exist at all. It acts as if it's not there. So what can we do with this? Well, we can go back to the integral one example. And now we can use arrow choice. When the condition is true, we activate the integral. When it's false, we don't. And the integral runs and is active when it's true. And it's not, and it's totally off when the condition is false. And unlike where traditional arrows might have a time leak due to this, because the integral is kind of semi-active in the background, with non-interfering choice, there is no leak. So non-interfering choice actually allows us to do one other cool little thing, which is rowized recursion. So recursion in FRP typically comes in two forms. There's value level recursion and structural recursion. So value level recursion is basically just a loop operator. It allows us to do something like a fixed point on a value on a stream in the signal function realm, in the arrow realm. Structural recursion uses the native language's choice, totally outside the signal function. So here we have an example where we're going to have a program that will run a signal function n times. So we have a signal function from a stream of A's to a stream of B's, and we'll turn it in one from a stream of list A's to a stream of list B's. So our recursion is on some int, some n, that is outside the arrow itself. And so in this case, you can imagine maybe n is 3, and so we'll start with the recursive case. We split our input into a head and a tail, and then the recursive case expands to another version of the recursive case now, because n was 3, and then it happens again, and finally we get our base case. And this whole thing, even though I've kind of zoomed in and confused it a little bit, is one static arrow, right? It's one static structure for the whole thing. The structure is not dependent on the values on the wires, like with switch. It's only dependent on a value outside of the arrow structure. So arrowized recursion is a little funny. As much as I've been advocating a totally static design, it's a little dynamic. So here, we're going to say, let's take our same signal function. Instead of running it n times, we'll run it some dynamic number of times based on how many elements are in the input list. So in this case, we can imagine our input list has 2 elements. So we run the recursive call. Once again, we have 1 element left in our list. When we get to we split on either an empty list or a head and a tail. We run it again. And maybe this time the list is empty. And so we take the top branch. And that works. The arrow structure is not technically static, but we call it predictably dynamic. There's one signal function that we're running some dynamic number of times. It's not exactly static, but it's good enough for optimization. So, the benefit of static arrows, or predictably dynamic arrows, is that we can optimize them very nicely. So we'll take a look at a particular optimization scheme, which is causal commutative arrows. So Liu Cheng and Hudak introduced causal commutative arrows, or CCAs. And they can be heavily optimized. You get massive performance increases, 10, 40 times, even faster in some cases. They do not allow switch. They do not allow higher order arrows, but they do allow choice. And in fact, they can even allow non-interfering choice. That extra law doesn't pose much of a problem, except that arrowized recursion is not supported by default. So we added that in. But first I'm going to take a quick look and explain how CCA works. So when you have these extra laws of causality and commutativity, what you can do is you can reduce a whole arrow structure by rejiggering it over and over into something that's either a totally pure function, or it's a totally pure function with one piece of state, one delay loop feedback state thing. So when we add in the ability to handle arrowized recursion, we call it CCA star. And we did a couple examples. We got some good performance results. So here are 3 different examples: a chained adder integral, a dynamic counter. Without going into a lot of details about what those are, I can say that we got good performance. This is a ratio improvement. So if GHC is going at a fixed rate, then how much faster did CCA star with Stream Fusion do? The chained adder only got about 4x performance increase. And we believe this is because it's a totally stateless signal function. It does have arrowized recursion, but it has no state. And we think that GHC is just doing a really good job on that one, even though for the stateful ones, we get a much better, more like 10x improvement. So in summary, we've introduced this idea of settability. It's a model for controlling FRP state. It gives us the ability to restart, to pause, to duplicate signal functions without actually changing the structure of the signal functions. We've introduced non-interfering choice, which allows for some new forms of expression, like the integral 1 example, and also arrowized recursion, like the run dynamic I just finished showing. And so we assert that switch is only needed for true higher order expression. You don't need it for these little performance cases where you need to stop a signal function from running or start one midway through execution, because you can do that with other static methods that still allow for these nice performance optimizations. So, thank you.
Are there any questions? Please come forward to the microphone.
Hi, Dominic Orchard from Cambridge. Very nice, very cool presentation and some nice results there. So I had a question just to help my understanding. Is the settable operation a bit like having a transistor where you have this other sort of channel coming in that can control what's going on between the input and output?
Yeah, it's sort of like that. Yeah, so the state that you get, you can save it and put it back in, and it totally kind of takes over what the signal function's doing for one moment, and it's all like that.
Thanks.
Sure.
I actually have the follow-up question, which is, are there other ideas of sequence design that
I'm sorry, say it again?
Are there other ideas of sequence design, like settability, that could be used?
Circuit design.
Yeah, I don't know. So I actually hadn't thought of it as a circuit design thing until the last question. As transistors in quite that way. Yeah, I'm not sure. That's something I'd be interested in talking about, though. Thanks.
Hello. Does this CCA optimization, do you have to have your own little compiler for it, or can you get it to effect with GHC rewrite rules?
That is... so we've tried playing with template Haskell. We've tried playing with rewrite rules, and nothing has been satisfactory. We're still trying to figure out how to get good performance with CCA in kind of a very general way. For now, there's a template Haskell CCA library that you can import and just kind of attach on, and there's I have a branch of that which supports the rowized recursion.
Okay, yeah. Please talk to me after.
Sure, great.
All right, let's thank the speaker again.